So far, this is the total variance if you have more than one dimensions. But for each direction, we want the direction vector to be unit bound. So just for recap, if you have more than one dimension, if you have more than one dimensions, then the W1 coordinate is this, W2 coordinate is this, and so on. And this is the projected point if we use k dimensions. Okay, why I पहले हमने जो वेरिएंस की डेफिनेशन दी थी वो यहाँ पे स्क्वायर था.
Yes.
लेकिन अब चूंकि ये भी वेक्टर है, ये वेक्टर इज अ नॉन स्क्वायर. अगर मैं इसको कंपोनेंट वाइज लिखूं तो दिस इज द फर्स्ट कंपोनेंट माइनस फर्स्ट कंपोनेंट स्क्वायर, सेकंड कंपोनेंट माइनस सेकंड कंपोनेंट स्क्वायर एंड सो ऑन. Which is और अगर मैं जस्ट इसको ऊपर अप करके लिखूं, this is simply W transpose this thing W1. This summation is still outside.
No.
Okay, so this thing becomes this summation, then for W1, then for W2, W3, and so on. Yes. Then I can swap this summations J and I this way, and then I can extract this Wj out, and this thing is the total summation. This is the famous matrix S that we saw last time. So this is the total variance.
Right.
And the total variance को sum की form में वैसे लिखा हुआ है, अगर मैं expand करके तो this is the total variance. Yes. This is the variance in direction W1. This is the variance in direction W2. This is the variance in direction WK. The goal is to find out the minimum K and find out these directions such that this number is maximized. But remember, these vectors, they must be unit vectors. Their scale should not scale this should not be the scale of W that defines the variance. It should just be direction vector. It must be unit vector. Make sense? If I make a Lagrangian of it, this becomes W1 transpose S1, W1 plus W2 transpose S1. Sorry, this is S W2 plus WK transpose S WK plus lambda 1 minus W1 transpose W1 plus lambda 2 1 minus W2 transpose W2 plus lambda plus so on plus lambda k 1 minus WK transpose WK. That's a Lagrangian. If I differentiate the Lagrangian to find out W1, I will differentiate this with respect to W1 and put it equal to 0. Yes. If I differentiate everything with respect to W1 and put it equal to 0, remember this term goes away, this term goes away, these all terms go away. Yes? And the derivative with respect to W1 becomes this, SW1 minus lambda W1, and I put it equal to 0, lambda 1. So SW1 is equal to lambda 1 W1.
Yes.
Similarly, if I differentiate this with respect to W2, I will get the same W2 with SW2 is equal to lambda 2 W2. SW3 is equal to lambda 3 W3. Now the question is, so now we see each and every direction that is going to maximize the variance is the direction of eigenvector of S. And S is completely determined by the data. You give me data, I can compute the S. So compute all the eigenvectors. Now the question is, which eigenvectors out of several eigenvectors, which k eigenvectors to pick? बाद में हम define करेंगे how to choose k, but let's say the k is given. If I am given that choose the best two directions, which two directions you will pick? Make sense? Now remember, if W1 is the eigenvector corresponding to eigenvalue lambda 1, and W2 is the eigenvector corresponding to eigenvector corresponding to eigenvalue lambda 2, then you can see that the variance W1 transpose S W1 plus W2 transpose S W2 is actually equal to lambda 1 plus lambda 2. Make sense? Because if I multiply W1 transpose here, lambda 1 यहाँ पे आ जाएगा. If I multiply W2 transpose here, ये समझ आ रही है ना? अगर मैं इसको लेफ्ट साइड से W1 ट्रांसपोज से मल्टीप्लाई करूं तो W1 ट्रांसपोज से मल्टीप्लाई कर दूं. It will become W1 transpose S W1 is equal to lambda 1 because W1 transpose W1 is equal to 1. Similarly here, and if I add these two equations together, I will get this number plus this number is equal to lambda 1 plus lambda 2. Yes. Which means if I choose two directions of corresponding eigenvalues. Make sense? Now the question is, if I am allowed to pick exactly two directions, what two directions will I pick? Obviously the two eigenvectors for which the eigenvalues are the maximum, because their sum is defining the total variance that I capture. Make sense? Now, so if I'm going to pick the three directions, I will pick top three directions in priority. If I'm going to pick the only one direction, I will pick the one with the highest variance, highest eigenvalue. If I'm allowed to pick two, I will pick top two, top three, top four, top five. Why? Because जो डायरेक्शन मैं पिक करूंगा उनके corresponding जो आइगन वैल्यूज हैं उनका sum is the variance that I have captured, and I want to capture the maximum variance. So I will get the maximum out of the available eigenvalues. Clear? Now the second question is how to choose K. How many top eigenvalues should I pick? If I want zero error, if I want the reconstruction exactly, then I should pick all the directions for which the variance is non-zero. I will pick all the vectors for which the eigenvalues are non-zero. Then I can cover the 100% of it. If I want, if I can afford 1% loss of information and I can cover 99% of the variance, then how many eigenvectors should I pick? I will pick eigenvectors in order incrementally. For example, I will pick first eigenvalue, the top one, and I will see the first eigenvalue captures the variance of how much of the total, which means lambda 1 is what fraction of all the sum of the lambdas. If it is equal to 99, then I am good with just one vector. Otherwise, I will pick lambda 1 plus lambda 2, where lambda 1 is the topmost, lambda 2 is the second one in ascending order. Then if the sum of these two covers the 99% of the total, then the directions are two. Otherwise, I will keep on moving and I will see, okay, let's say 9 vectors or 39 vectors, they cover the 99%. Or you can lower the threshold to 95% and stuff. Make sense? Why you really want or sometimes can afford to have a little loss in the information? Sometimes you consider that the actual data has noise, okay, and noise is random, and the magnitude of noise is, if the magnitude of noise is not very large, then in that direction in which the noise is being added, that will be the direction in which the variation will be minimum. And if you throw that direction, that direction will be, the hope is that is the direction in which the eigenvalue is very small. If you discard that direction or many of those directions, you actually suppress the noise. That is in the hope that the noise is actually making a little variance in the data and you can discard that direction, and which will eventually give you the noise to be suppressed. Make sense? But be careful. Sometimes throwing this direction which corresponding to which the eigenvalue is non-zero but very little, sometimes degrades the classification performance in a great way. And here is an example given in the book of Flda Hart pattern classification. The example is the following. This is just a concrete example of saying that whenever you throw the direction with the minimum eigenvalue, you always remove the noise. Sometimes you remove the very important information from classification. And here is the example. The example they gave in their book is that let's say you want to classify O, the image of O, OC or O. Let's say you want to classify O with Q. Make sense? And it may happen that you have a lot of images of O and you have a lot of images of Q. And then it may happen that the direction that you throw, the direction in which the variation is very small, is actually the direction that captures this thing. And this is actually the discriminative property between this and that. And you throw that by assuming that this is the noise. So, I mean, you have to be very careful if you are very sure about the data, that the data indeed has noise, then, I mean, throwing the least important eigenvector with respect to the amount of eigenvalue is not always suppressing the noise. It is the hope that it will suppress the noise. In certain situations, you may end up throwing important information.
Same is the case with A, right?
Sorry?
Same could be the case with A.
I mean, yes, I mean, the data that has, you consider that these things are noise and actually these are discriminative features. They are not noise. It can happen. Yes.
हमारे पास तो क्यों का जो उसके साथ लगा हुआ है वो बाहर से उस डायरेक्शन का एनालिसिस सबसे ज़्यादा क्यों नहीं होगी
सबसे ज़्यादा
क्यों नहीं होगी वैसे क्यों नहीं होगी ये कम आपने क्या लिखा सकता है सबसे कम वाली एरिया वाली हो ये सबसे कम वाली एरिया वाली उसकी क्यों निकलेगी ऐसे नहीं सकता कि इसके सबसे ज़्यादा किसके एयर में लगता है कि कौन सी एरिया सबसे ज़्यादा होगी कौन सी थोड़ी होगी ये किसी को लगता है
So let's say I have a lot of so अगर मैं इसको intensity form में लिखूँ ना intensity form में लिखूँ तो that would be a vector O. I have several O's. सही है? Then I have Q's. अगर उसको intensity form में लिखूँ I have several Q's. ये कुछ पिक्सल ऐसे होंगे जो इसको ना describe कर रहे होंगे. Yes? बाकी अगर मैं लिखूँ I want to capture O because this is something in which the intensity is varied a lot. So these are the pixels in which the variation will be very, very small. Several O's are there in which this is not there. Some several Q's are there in which a very small portion is covered by that. So this might be a noise that is disturbing the information. So you end up finding that. Make sense? Okay. One important question about this is are these, because in the formulation we never considered that the bases are orthonormal. We consider that the bases are normalized, they are unit vectors, but we never consider that they are actually orthogonal. Yes? In fact, this matrix S is symmetric. This matrix S is symmetric due to the fact that it is an outer product of a matrix with itself. It is a symmetric matrix, and for symmetric matrix, the eigenvectors are orthogonal. So you need not to go and see whether they are orthogonal or not. If they are symmetric, you get the orthogonal matrix, orthogonal vectors. Say it. Number two, is it possible that some of the eigenvalues become negative?
No?
Is it possible that some of the eigenvalues become negative? Remember the eigenvalue, the amount of it represents the variation or the variance. Is it possible that some of the eigenvalues, because if you come up with a matrix, you can have some positive eigenvalues, you can have some negative eigenvalues, you can have some zero eigenvalues. Even you can have complex eigenvalues also for a matrix with real entries. In this particular case, because the matrix is symmetric, so that's a theorem, because the matrix is symmetric, all the eigenvalues are real, number one. In this matrix is not just symmetric, it is positive semi-definite matrix. A positive semi-definite matrix is a matrix which is symmetric and has certain properties. I'm not going into those properties. This matrix has that property, which means all the eigenvalues are non-negative. Either they are zero or positive. So there is no question to consider, oh, there might be an eigenvalue that has negative sign. What do it mean that a particular direction has negative variance? So no such question will arise. Make sense? So this is completely okay to go with that. Just sort the eigenvalues, sort the eigenvectors accordingly. Pick the topmost eigenvectors that cover the maximum threshold of the variance you want to cover. Let's say 95%, 98%, 99%. और ये बड़ी एक्सट्रीम एग्जांपल्स हैं जिनमें कहा जाता है कि ये क्लासिफिकेशन को थ्रो आउट कर सकते हैं कुछ आइगन डायरेक्शंस को. In practice, I mean, people work with 98 or 97% variance capturing, and in practice, even with that, the classification accuracy in most of the cases works very well. Make sense? If you want to be very, very curious, if you know something about data, if you don't want to lose a lot of information, you can go with 100% reconstruction. Still you end up by reducing a lot of direction that has just no information in it. Make sense? Okay, that's all about unsupervised dimensionality reduction. By the way, why it is called principal component analysis? These eigenvectors, they are called principal components. I mean, they are named as principal components. Okay. I mean, the top one eigenvector is the first principal component, the second eigenvector is the second principal component, and so on. So, because they are named as principal components, this kind of analysis is called principal component analysis. Clear? This is unsupervised dimensionality reduction due to the fact that we never use the labels. We never use the class labels. Like we have not labels. We do not have labels. We just have data, we want to compress the data.
Yeah.
And we can always decompress without thinking what classification. I mean, when compressing and decompressing in this particular way, we never considered classification at hand. Our goal was never to have a better classification accuracy. Our goal was to compress in a way that you do not lose much. Make sense? Supervised dimensionality reduction. One instance that I'm going to cover today for supervised dimensionality reduction is FLDA. By F, I means Fisher, L means linear, D means discriminant, and A means analysis. Analysis. Fisher's linear discriminant analysis. Clear? And this is supervised dimensionality reduction technique. And the goal here that will come very obvious after a while. The goal here is not to reconstruct the data. The objective here is not to represent the data that a lot of information is maintained in the original features, so that I can reconstruct my original data whenever I want. This is not the goal. The goal is to come up with the features from the features. Given the features, come up with the new features such that it improves the classification. It discriminates different classes very well. So if your original features has less power of discrimination between two objects of different classes, come up with a new set of features that has more power of discrimination under certain assumptions. If I will be having time, I will tell you the assumption at the end. So come up with the features that has power that different classes, they are better discriminatable if we use the new features.
Yeah.
But we can never reconstruct our data back.
Achha.
So the goal is not reconstruction. The goal is, this is not compress, decompress. This is simply compress, improve classification.
Achha.
Make sense? Dimension decrease only, this is dimensionality reduction. So compress the data with the goal that improve classification accuracy. This is not compress the data with the goal that we can decompress all of this. So it will use the classification labels, it will use class labels during the process of reduction, because the goal here is to improve the classification accuracy. Come up with the new features, come up with the smallest number of features, make new features, very small, so that the classification improves. Make sense? And what is a measure that classification will improve? वो measure मैं भी आपको बताता हूँ. Clear? This was introduced by a very famous statistician Fisher. Back in I guess 90s or 80s, I don't know. It's a very famous statistician. It's a big name in statistics and machine learning. Fisher. Okay, why it is linear? We will see that again the projection will be achieved again by multiplying or taking the dot products, which means that's a linear transform. Whenever you transform a vector to another vector, but that transformation is achievable through a matrix multiplication, that transform is called linear. So here we will see that the actual transformation from xi to its projection is actually achievable through a linear transform. So it is called a Fisher's linear. Now, Fisher linear over discriminant because it is going to make new features in which their discrimination is very high. Analysis means that we are going to analyze. So Fisher's linear discriminant analysis. Makes sense? And the goal is the following. Let me describe that goal. First in pseudo English and then we will write that. And control the goal. Project. By project I mean transform. Okay, transform. Project the data points such that projects are really as I find out a subspace such that the data points of a class of every class become close to each other, closed to each other. Within the class and away from
The other classes.
the points of other classes.
Nice.
सही है, this is the goal. The goal is कि आप डेटा को इस तरह से प्रोजेक्ट करें, ऐसी सबस्पेस फाइंड आउट करें. प्रोजेक्ट लीनियर प्रोजेक्शन है, लीनियर ट्रांसफॉर्मेशन है, सबस्पेस ऐसी सबस्पेस फाइंड आउट करें. एक क्लास के जितने भी पॉइंट्स हैं, एक क्लास के जितने भी पॉइंट्स हैं, वो आपस में करीब आ जाएं. They become compact. A class become compact. सही है? लेकिन जो दो क्लासेस हैं, वो आपस में दूर हो जाएं. Make sense? So you want to achieve highest discrimination. ये क्लास इस क्लास से बहुत दूर हो. But then you want कि हर क्लास आपस में बड़ी सही हो. वो ऐसे जुड़े हुए हो सारे. Make sense?
सर क्लोज लिखने का क्या स्पेशल होता है इसका?
मतलब closed और closed in the sense of distance. या closed को भी मैं mathematically define करता हूँ. Closed means कि एक क्लास का जो variance है वो कम है. All the points they are not scattered along. Within the class, yes, this is a measure of distance of variance.
हम लास्ट में देखा था कि अगर 3D प्लेन है तो उसके अंदर 3D अगर प्लस बेस है तो उसमें एक क्लास के सारे एलिमेंट्स एक ही प्लेन पे आते हैं.
एक प्लेन पे आ जाए.
एक प्लेन पे आते हैं.
ठीक है.
और दूसरी क्लास के किसी दूसरी प्लेन पे आते हैं.
नहीं हमारे पास सबस्पेस एक ही है. यही तो गेम है. क्या सबस्पेस फर्क नहीं है. ये ऐसा नहीं है. ऐसा नहीं है कि
एक ही प्लेन.
ऐसा नहीं है कि आपने एक क्लास को किसी एक ट्रांसफॉर्म करना, दूसरे को किसी और डब्ल्यू से ट्रांसफॉर्म करना. ऐसा नहीं है. You have same subspace. You have to come up with one subspace. आपके केस में come up with a plane. उसी प्लेन पे दोनों फेंकना है. लेकिन फेंकने के बाद यानी प्लेन एक ही होगा. Subspace is common. You come up with a common subspace. एक subspace है. Different के लिए different subspaces नहीं है. और उसकी वजह ये है कि जब टेस्ट पॉइंट आएगा उसको हम फिर किस subspace से बुलाएंगे. इसको इसमें रिप्रेजेंट करेंगे, उसको इसमें रिप्रेजेंट करेंगे. So come up with a subspace, common subspace. उसी सबस्पेस में पूरा डेटा प्रोजेक्ट कर दें. But it just so happened that after projection, the projected points of class 1, labels आपके पास हैं, they are very close to each other. And the two classes, they are away. Make sense? Yes, no?
सर हमने पीसी में पढ़ा था कि ना किसी वजह से एक स्पेसिफिक केस के अंदर कंपोनेंट्स बढ़ भी सकते हैं. सर इसके अंदर ऐसा
पीसी में नहीं पढ़ सकते. वो तो था RBF नेटवर्क्स.
आगे
RBF नेटवर्क्स पीसी में नहीं पढ़ सकते.
पीछे आप आगे नेटवर्क के यूज करके क्लस्टरिंग करके उसके बाद पीसी में
Yes.
तो क्लस्टरिंग के अंदर इन सॉर्ट ऑफ बढ़ सकते हैं.
तो क्लस्टरिंग मैंने बिल्कुल नहीं कहा कि वो डायमेंशनल रिडक्शन टेक्निक है RBF नेटवर्क्स के कॉन्टेक्स्ट में. मैंने ये कहा it can be viewed as a feature transformation. I haven't used the word feature reduction. Feature reduction in the case if your number of clusters is smaller than number of dimensions, then feature reduction happens. लेकिन ये ऐसा नहीं है कि ये feature reduction technique है.
तो यहाँ पर ऐसा बस
पीसी में नहीं है, बढ़ेंगे नहीं. सही है जी? So let me explain this pictorially. Let's say these are the points of class 1. These are the points of class 1 and let's say these are points of class 2. are points of class 2. फिलहाल मैं 2-dimensional feature space की बात कर रहा हूँ, and फिलहाल मैं assuming कि मैंने इसको 1-dimensional subspace पे project करना है, and my goal is कि projection के बाद जो एक class के projected points हैं, they become close to each other, और जो दोनों classes हैं, they become far away. Which direction should you pick? एक तो ये इमेज डायरेक्शन में पिक कर लो,
Of course यही होगा।
फिर तो सारे एलिमेंट्स हो जाएंगे।
नहीं वो तो क्लोज आ जाएंगे।
फिर तो इसका मतलब है कि दो क्लासेस के जो मुख्तलिफ क्लासेस के पॉइंट्स हैं, दे आर नॉट फार अवे।
इधर कर लेंगे
ऐसे कर लें?
ऐड अपोजिट हां
Yes.
perpendicular
Okay, now you see all these points they make a blob here, a smaller blob, and all these points they are projected and make a blob here. ये blob जितना छोटा होगा और इन दो blobs के दरमियान जितना distance ज़्यादा होगा, वो वाली direction आप लेना। Now you get to know the idea of discriminant. You come up with the projections that discriminate the two classes the most. ये देखिए ना, इसमें ये वाला पॉइंट यहाँ पे आएगा, ये वाला पॉइंट यहाँ पे आएगा, बाकी सारे इसके दरमियान आएंगे। ब्लॉक नहीं है एक्चुअली, ये इंटरवल कह रहे हैं यहाँ। सही है? अगर मैं डायरेक्शन कोई और ले लूँ, तो ये वाला पॉइंट यहाँ पे आएगा, ये वाला पॉइंट यहाँ पे आएगा, तो ये इंटरवल लेंथ बन जाएगा।
हां
तो ये बात समझ में आई? मैं चाहता हूँ कि एक क्लास के पॉइंट्स प्रोजेक्शन के बाद उनका वेरिएंस ज़्यादा ना हो। Variance is very small. But then I want the two classes, they are far away. और ये far away को मैं mathematically define कर रहा हूँ. Two classes far away means what? एक क्लास का वेरिएंस कम है, उसका तो मतलब ये उसके जितने भी पॉइंट्स हम का वेरिएंस कंप्यूट कर लें, वेरिएंस मिनिमम होना चाहिए। दो क्लासेस आपस में बहुत दूर हैं, that means what?
हां
तो उसको डिफाइन करें। First understand this is our goal. Yes, no?
Yes.
Make sense?
Yes.
makes sense
First, let us define the within class variance. Let me define the within class variance of class 1, within class variance of class 2. For now, I am assuming two things. I have only two classes, it's a binary classification problem for now. And I am going to project it onto one-dimensional subspace. So I am assuming for now, I have binary classification problem. And I'm going to find out one-dimensional subspace that maximizes the discrimination. And original dimensions are D. Original dimensions are no longer 2. They are D dimensions. Later we will see, later we will examine that if we have multiple classes, more than 2, and we want to find out a multiple dimensional subspace, how to expand the idea. Make sense? Yes, no, please. Okay. So for now, binary classification problem. Original xi belongs to, it is d by 1 xi. Yes? Just for simplicity, I'm assuming this. The class 1 points, they are x1, y1, x2, y2. These are all the points of class 1. x, n1, y, n1. सही है? And similarly, class 2 के जितने भी points हैं, they are these. X. Should I use some other? So this is x11. सही है? Now we have x21. This is not square. This is the point of class 2, and this is the first point of it. And we have y1, 2. Then we have x, second point of class 2, and we have y2. Just notation. X n2. N2 means the total number of points in class 2 are n2. Okay. And then we have y n2. This is data of class 1, this is data of class 2. Yes? ये जो superscript है, this is not power. This is just to mention that this is a point of class 1.
सही
Clear? By the way, ये labels भी देने की जरूरत नहीं थी. Labels देने की जरूरत नहीं है, अगर हम सिर्फ लिखते हैं x1, ये ऊपर labels दिए तो हैं.
हाँ
Make sense? So labels are no longer required. Let me write this. C1. Yeah, let me have this data x as the following: x11, x21, xi2, x whatever, and of class 1. Some of these are of class 1, some of these are, and this is the data matrix. Yes? And let's say there are n1 points of class 1 and n2 points of class 2. Make sense?
ठीक हो गया
Okay, now how to define within class layer? Let me define the variation in class 1. Variation in class 1. Assume we have only one dimensional projection. This is the ith point of class 1 and it goes to, let's say, y. This y is not labeled. This is the coordinate. This is the projected coordinate. Should I use alpha or y is okay with you? Y, alpha likho? Okay, alpha. This is alpha I of class 1. Make sense? Yes, no? Yes, sir. Now, the variance of class 1 after projection is the following. I varies from 1 to n1, x I1, sorry, xi1 alpha I1 is the projection minus the mean of. This is the variance
of class 1.
of class 1. Make sense?
Yes.
After projection. And this is the variance and 2 alpha I2 minus alpha 2. This is the variance of class 2.
सिर्फ वो आपने x का लिखा हुआ है कि x1 और x2 फर्स्ट क्लास है फिर आपने
जिसका सुपरस्क्रिप्ट 1 है वो क्लास 1 का है, जिसका सुपरस्क्रिप्ट 2 है वो क्लास 2।
उसके बाद आपने जो लिखा छोटा नंबर n उसके ऊपर 1 क्लास दिया हुआ है
नहीं, ये nth पॉइंट है वो क्लास 1 का है, nth पॉइंट क्लास 1 का है। मैंने तो रैंडम कर दिया ना, पहला पॉइंट क्लास 1 का है, दूसरा पॉइंट है, आगे पॉइंट 2 है।
उसको मिक्स क्लासेस
मिक्स पॉइंट किसी ऑर्डर में जाएगा, ठीक है? Make sense? All am I saying that there are n1 points of class 1 and there are n2 points of class 2. Yes? Yes. This is the variance of class 1. This is the variance of class 2. I want the sum of it to be minimum. This is the variance. This is called width in class variance. And this is the number at the end of the day. I want this to be minimum. And I want between class variance to be maximum. Between class को डिफाइन करते हैं. I want कि हर क्लास के अंदर वेरिएंस कम हो. अगर हर क्लास का अपना वेरिएंस कम होगा तो उनका सम भी कम होगा. Yes. और फिर मैं कहूँगा कि दो क्लासेस के दरमियान between class variance should be high. Two classes they should be separated away.
Yeah.
And we will define a measure to define कि how to define two classes that are separate. Make sense? फिलहाल convince yourself that this is a measure of defining within class variance, and I want this to be small. Clear?
Yes.
Yes, no?
Yes.
One question. चलिए आगे? Okay. आगे चीजें ज़रा easy हैं, मुश्किल नहीं हैं. इसका आपको बताइए, इसको क्या करना है? इसको फौरन लिख देना है. W transpose summation I is from 1 to n1 xi1 minus x1 bar times xi1 minus x1 bar transpose times w1 or times w. Yes? ये तो पढ़ सकते हैं हम? ये पीछे में किया था. इसको रिप्लेस करें, इसको रिप्लेस करें, या मैंने क्या these things out. ये अभी मैंने पहली सबमिशन लिखी है, पहली बार. Yes, first one. जब सेकंड लिखेंगे plus, अब मैं सेकंड लिखने जा रहा हूँ,
Yes.
W transpose I varies from 1 to n2 xi2 minus x2 bar xi2 minus x2 bar transpose times W. Make sense? Yes, no? Yes. I'm just replacing this alpha with this one and then writing the square and then writing the outer products and stuff. Yes? I'm calling this matrix, which is completely computed from the data. I'm calling this as S1. And I'm calling this matrix, which is again completely computed through the data. I'm calling this as S2. Sahi? So the within class scatter is W transpose S1W plus W transpose S2W. I want this to be minimized. And if you see, I can write this as W transpose S1 plus S2W. Make sense?
Yes.
And I'm calling this S1 plus SW as SW within class scatter,
Acha.
which is the scatter matrix of class 1 and then scatter matrix of class 2. Just add them together and you have SW. One matrix. So far so good?
Yes.
And I can compute this SW from data. That's it. By the way, to compute SW, I need the label information. Because to compute S1, I need all the points of class 1.
Yes.
To compute S2, I need all the points of class 2. So I'm using label information there to compute S1 and S2. Yes?
Yes.
Okay, so minimize W transpose SW. ये है within class variance. अब हम जाएंगे between class variance को define करने. Make sense? इसको minimize करेंगे, उसको maximize करेंगे. और फिर देखेंगे कि वो W कौन सा होगा जो इसको minimize करेगा और उसको maximize. Yes, no?
Yes.
Is W? Is W?
Yes.
कैसा होगा यार तो कैसा होगा वो नहीं होगा क्या कहते हैं
सर वो उनका मोटिव है इस चीज़ वो इस तरह वो बस अपनी के लिए ब्रांडिंग के लिए अपनी ब्रांडिंग वगैरह के लिए अपने ब्रांडिंग के लिए बस मतलब अपने आप को शो करेंगे
ठीक है सही है This is class 1. This is class 2. I want to know how much these classes are away from each other.
Yes.
There are several ways of defining this method. There are several ways. One is okay, I pick a point in this class that is closest to this class, k points. I pick a closest pair from this and that and then define the distance between them. I call that is a between class equation.
Yeah.
That is one way. Another way is I compute the centroid of this class and I compute the centroid of this class and I take their distance and I say this is the between class variance.
Yeah.
Make sense? Another way is I compute the centroid of the data
Acha.
and I compute the distance of this centroid from the center and then I compute the distance of this centroid from the center, and that's again another way of computing how the two classes are far away from each other. Make sense?
Acha.
So there are several measures. It turns out that this measure, that you compute the centroid of the data and then compute the difference of this point from that and this difference of this point from that and add them up. This is mostly used as a between class variance.
Acha.
And one thing is, अभी हम थोड़ी देर बाद देखेंगे, if we have more than two classes, then actually this pairing all the distance become very high.
Acha.
कि अगर मैंने pairing ढूंढ के शुरू करना है, कि मैं इसका आपस में sum करूँ, rather than I compute the centroid of the data, then I compute this distance, that distance, and that distance, and I compute this as a measure of between class variance.
अच्छा.
Make sense? So the between class variance is defined as following: alpha 1 minus alpha plus alpha 2 mean minus alpha. This is the distance of class 1 centroid from the overall centroid. This is the distance from class 2 centroid from the overall centroid. Yes? And this is how we define the between class variance. Yes? I want this number to be maximum. There is no sum outside. There is no sum. No data points are involved. Once you have means computed, that's what you want to minimize. You want to maximize this. Clear? Yes, no? Yes. Now, allow me to write this thing as W transpose X 1 bar minus X bar X1 bar minus X bar transpose W1. This is the first quantity. By the same argument, you can unravel this square and you get this thing.
Yes.
This is the mean of the total data. This is the mean of class 1 data points. Yes? Plus W transpose X2 minus X bar into X2 minus X bar transpose W. Yes? Make sense? Let me call this matrix as B1. Let me call this matrix as B2, which is completely computable from the data. Then the between class scatter is simply W transpose B1 plus B2 W. Yes? And you can compute B1 from the data, you can compute B2 from the data. Yes? I'm calling this total matrix as SP. Between class scatter, within class scatter. You can compute SP and SW from data. To compute SB, you need label information. To compute SW, you need label information. Yes, no? So far, so good?
Yes.
Okay. Official criteria. Now, you want to minimize this and you want to maximize this.
Yes.
And Fisher came up with the following criteria. Fisher says, okay, maximize maximize this. Make sense?
Yes.
And this criteria is known as Fisher's criteria. Fisher ने कहा कि वो W जो इस रेशो को मैक्सिमाइज करेगा, this is the W जो के क्लासेस को आपस में कॉम्पैक्ट करेगा और बिटवीन क्लास वेरिएंस को बढ़ा देगा. Now you end up, yes.
या मैं इसको उलट करके मिनिमाइज कर सकता हूँ.
उलट करके मिनिमाइज कर सकते हैं. Yes. Now once you have this, you can play with it. उलट करके मिनिमाइज कर सकते हैं, माइनस करके मिनिमाइज कर सकते हैं. Yes, no. So far, so good?
Yes.
Remember, SB and SW, they can be computed from data. और
Yes.
सिर्फ data के. Yes?
Yes.
अब सवाल ये है कि इस रेशो को मैक्सिमाइज कैसे करें. और यहाँ पे सभी का सवाल आता है, मेरे पास बहुत सारी चॉइसेस होंगी. हम वन बाय वन कैसे चेक करेंगे? तो मैं आपकी तरफ से सवाल करके अब जवाब ये देगा. दे सभी? ओके, एसपीएम में हमने इस तरह की सिचुएशन देखी थी फिर में जब हमने रेशियो को मिनिमाइज किया और उसमें हमने ये किया था कि बजाय दोनों एंड्स को अप और डाउन करने के लिए फिक्स वन एंड एंड देन यू प्ले विद द अदर. सो आई एम गोइंग टू रीफॉर्मुलेट दिस प्रॉब्लम एज maximize W transpose S V W subject to the constraint that W transpose S W is fixed. You fix it to any number, not just to any number. You fix it and then you keep on maximizing this. This is equivalent to maximizing this ratio. सही है जी? But now it is a constraint optimization problem. You know how to deal with constraint optimization problem. Just write the constraint in the form that Lagrangian required and then just put up the Lagrangian and you will do. Make sense? Okay. So, should I erase that thing?
Yes.
Do not ask me to derive these things again. अगर ये अभी मसला है तो पूछें. Is that okay?
Yes.
Okay, so I can write this as 1 minus that equals to 0. Yes? And then the Lagrangian is W transpose S being W plus Lagrange multiplier 1 minus W transpose S W. W equals, I mean, this is the Lagrangian function with Lagrange multiplier lambda or alpha or whatever. Alpha we use करके लंबा हो गया हम आगे use कर. Now differentiate this with respect to W and see the condition. What condition occurs? So differentiate this with respect to W, you get SVW minus lambda SW